Okay, welcome to video 2 of this lesson. Having described how the cardiovascular system sort of works globally, now I want to dive into how the vasculature works. And the first thing I want to talk to you about are the different types of vessels, some of their characteristics, and why they do what they do. You might want to pay particular attention to this information because it integrates really well with your histology lessons, and some of this will supply you with some functional reasons why the structure of these vessels is what it is. Okay, so first of all, we have our different classifications of vessels here. We have the aorta and the arteries, we have the veins and the vena cava here. We have the arterioles, which are really more smaller arteries. We classify these sort of as microvessels, but they're part of the arterial compartment. And we have capillaries and we have venules, all smaller. These are all larger vessels. And we have different characteristics of these tissues sort of lined up. You know, how much elastic tissue is there, how much smooth muscle is there, how much fibrous tissue, etc. Okay? So you can see how this would integrate really well with histo. So the first thing you'll notice, the diameter decreases as you go down toward the vascular beds, right? That makes perfect sense. Your arteries are smaller than your aorta, your arterioles smaller than your artery. You're gradually getting smaller and smaller. Okay? The walls become thinner as you go down toward the vascular beds. Okay? And that should make perfect sense as well. And here you can see the wall thickness, so that varies with the size. Now, the arteries have relatively more musculature than the other vascular tissues, the veins and certainly the capillaries. You will note in particular how muscular the arterioles are. And that's because your arterioles, when we talk about vasoconstriction, I mean the arteries constrict, but the real reason why you constrict your vessels generally is because you want to increase resistance to blood flow. That is, you want to cut blood flow down. So the smaller your arteries get, the less blood flow there is because you have a higher resistance to flow. So when we talk about resistance to flow through the system or through a particular bed, although all these arteries contract, the arterioles are where the resistance increased the most. And I'm going to show you that, why we know that in a moment. So we call these arterioles the stopcocks of the system. That is, when your system really wants to restrict flow to a bed, what it really does is it constricts the arterioles. And the arterioles are responsible for almost all the increase in resistance to flow that you see to a particular vascular bed. The arterioles constrict, the resistance to flow goes up and the flow goes down. The arterioles dilate, the resistance to flow goes down and the flow goes up because it's easier for blood to flow through a bigger arteriole or bigger vessel. Okay? So these are like stopcocks in front of each vascular bed. Okay? You also see the elastic tissue is reasonably high in the aorta and the large arteries. These need to expand quite a bit more than these other vessels because you've got a lot of blood being shoved into them all at once. Okay? The capillaries are small. The wall is really thin. In fact, it's mostly pretty much just solely endothelium. And this is where exchange of nutrients and oxygen and such takes place, so that should make sense to you. These walls need to be extremely thin because that exchange takes place via diffusion, and you guys know the distance of diffusion has to be relatively small. Okay? And then finally we have the venous compartment. Here the blood is returned to the right atrium through the veins. The venules dump blood into the veins, and the veins dump blood into the atrium. So you have more venules than you do veins. You have more veins than you do, the vena cava basically is what dumps into the right atrium. So you have a gradually decreasing number as you get closer and closer to the heart. And they get gradually bigger and bigger. All right. So blood returned to the right atrium. and it flows through the heart, right? So we have oxygen, poor blood flowing through the vena cava into the right atria, and then the blood flows through the right atrium to the right ventricle from high pressure to low pressure. During diastole, you guys know that, the heart contracts, and the right ventricle pumps the blood into the lungs, where it picks up oxygen. The blood is then returned to the left atrium and the left ventricle during diastole again. And then you start systole again, and the blood is once again pumped out of the left ventricle into the aorta, and it's distributed to all parts of the body, right? Okay. So, now let's talk a little bit about how we classify the vasculature in the body. Having said that, the blood is shoved out into the arteries. We can classify the vessels a number of different ways. But the first thing I want you to know is that the blood flow in all parts of the cardiovascular system is the same at steady state. It's the cardiac output. You can take the output of the left heart, and if you add up the flow through all the arteries, it'll be the same as the cardiac output through the left heart. If you add up all the blood flow through the capillary beds, it'll be the same as the blood flow through the arteries, which was the same as the blood output of the left heart, the cardiac output. If you add up all the flow through the veins, you get the same blood flow that you did through the capillary beds and the arteries, and then all that blood is dumped into the right heart. So when we look at this graph, for instance, we have pressure on the y-axis, and we have that pressure in different vessels of decreasing diameters, at least through down to the capillaries, okay? So these are different types of vessels in the body, but the blood flow in this graph is the same. We talk about the blood flow through the aorta, 5 meters per minute. The larger arteries, that means I add up all the flow in the larger arteries, the flow is the same. The flow is the same in the arterioles as it was in the aorta, okay? You add them all up, the flow is the same. So, so this is the difference, this is the pressure in these arteries, but remember it's the pressure at the same flow with the changes in size here. When we say the vessels are getting smaller, the flow is the same when you add them all up. So that blood flow, again, obeys Ohm's law. 90% of life is showing up, 90% of the rest is Ohm's law. Flow is equal to the pressure in the arteries minus the pressure in the veins, divided by resistance. In any section of the cardiovascular system, this works, okay? If you're talking about blood through a particular bed, you look at the perfusing pressure in the arteries feeding that bed, you measure the pressure in the veins coming out of that bed, that difference in pressure will be, divided by the resistance to flow through that bed, gives you the flow through the bed, okay? So we can do that here. If you look at, we can do that here. So if you look at any particular compartment here, if you look at the difference in pressure on one end of the compartment compared to the other, you know the flow through that compartment is the same everywhere. This is constant, 5 liters per minute normally, okay? If the difference in pressure across any segment of this system is large, that means that there's a large resistance to flow, because this times this has to equal this. If this is constant and this is large, then this must be large. On the other hand, assuming this is constant and the delta P is small, then this must be small, because this times this must equal this, okay? So if we take that and we apply that here, we look at the aorta and we look at the big arteries and we look at the pressure at the end of our big arteries, at the end of that compartment, as our diameter starts to decrease down to the arteriolar level. And we look at the pressure in the aorta, they're virtually the same. There's almost no difference between them, okay? And what that means is that delta P from the beginning of the aorta to the end of the large arteries is relatively small. So if delta P is small, then that means that the resistance must be small as well, okay? On the other hand, if delta P is large, then we must be looking at a large resistance to flow. So look at the resistance to flow, look at the pressure at the beginning of the arterioles as the blood just starts to enter that arteriolar compartment. And look at the pressure at the end of that compartment. That's a big difference. That's like 75 millimeters of mercury. So what that tells you is that the resistance to flow is really big in this compartment. Delta P is big. The flow is 5 liters per minute. It's constant. So the resistance must be big. So this tells us that most of the resistance in this system is coming from the arterioles. And when we change the resistance in the system, what we're really doing is we're constricting those arterioles. That's the compartment that counts, okay? So the resistance to flow is high in the arterioles, and that's where the regulation of flow takes place, okay, through any particular bed. And the resistance is strongly determined by the radius, okay? There are a lot of things that determine resistance. I'll expose you to Poiseuille's law in a second. But the first thing I want you to notice is that what we have when we look at the calculation for resistance, we have the radius raised to the 4th power in the denominator of this equation. That means that a small change in the radius gives you a large change in resistance. So a very small change in the radius of the arterioles will give you a big change in the resistance. If I want to increase the resistance to flow, if I just vasoconstrict a little bit, I get a big change in resistance, okay? On the other hand, if I get a little bit of a dilation, I get a big decrease in resistance to flow through any particular bed or through the system itself, okay? All right. So we can classify our vessels by compliance. So compliance is the change in volume in any particular structure divided by the change in pressure that it took to change the volume. So here I have pressure on the x-axis, I have volume on the y-axis, and notice in my veins, the volume goes up as the pressure in the vein goes up. Or another way of saying is that as the volume goes up, the pressure goes up. Okay? They co-vary, and the amount of change that you get in volume for any given change in pressure is defined by the compliance. So we get big changes in volume. We get a big change in volume in veins for a relatively small change in pressure. You know, let's say 10 millimeters of mercury here. So that tells us that the compliance in the veins is high. So on the other hand, the compliance of arteries is relatively low. If we take the same change in pressure here, let's say this was 15 millimeters of mercury. If we go up 15 millimeters of mercury here in the arteries, we aren't increasing that volume nearly as much as we increase it in the veins. So that tells us that the compliance is low in the arteries, it's high in the veins. And the other thing I want you to notice is that over the physiological range, which is more or less bounded by these blue lines, that the compliance is more or less constant. We consider it, for the purposes of the cardiovascular system, to be linear. Okay? So that means that the compliance is the same over the physiological range of pressures in veins and arteries. Okay? And it's not only the same, but it's relatively high in the veins and relatively low in the arteries. And that has consequences for the cardiovascular system. And I'll explain that toward the end of this lesson, why that is. We can classify these vessels by volume. So this is the relative percentage of the blood volume that you'll find in any given compartment in the cardiovascular system. You'll notice that the arteries and the arterioles only have 11%. And in fact, if you just consider the arterioles, it's much lower than that. So the reason I point that out is because we're going to talk a lot about constriction of arterioles. And I don't want you to get the impression that you're changing the distribution volume within the system all that much just because you decrease the volume of the arterioles. Okay, the arterioles don't account for, they don't have a lot of volume in them at any one time. So when I constrict the arterioles, I'm really not decreasing the volume in the arteries all that much. Okay, I'm not shoving a lot of volume out of the arterioles and into other compartments. Okay, and that'll become important to you later. But what I really want you to notice in terms of the volumes is how much volume the veins have. They contain almost 2/3 of the blood volume in the system. That's because their compliance is really high. So at a relatively low pressure, they can contain a really high volume. And so there's a really high volume there. And again, this has implications which we'll discuss later. If I were to hemorrhage out a bunch of blood, the veins would actually constrict and you get venoconstriction, and that would take the amount of blood in the veins and it would decrease it, and it would like be a shot of blood into my arterial system, and it would help me maintain mean arterial pressure. We'll address that later, not so important now, but I do want you to notice that most of the blood volume is contained in the veins, okay? And we actually consider it to be sort of a reservoir for blood that we can draw upon when we need it. All right, we can classify these vessels by velocity of flow. So this can be a really confusing issue because people get velocity and blood flow mixed up, okay? So first of all, let's look at a small vessel and a large vessel. And let's take a little section of blood in each one of these. And in fact, if you want, you can consider these blue boxes to actually represent a single molecule of water, okay? Think about that, okay? It's like a single molecule of water, okay? Now, blood will flow, water will flow, blood's got water in it, from high pressure to low pressure through each of these vessels, okay? So, as that happens, water will move from here to here over a certain distance. And you will notice that that water molecule moved the same distance in each of these vessels. So we say that the velocity of flow is the same in both of these vessels. But notice that this is a much bigger vessel than this. So you know that the blood flow is much higher through this vessel than this. Okay? So the flow is high here, but the velocity of flow is the same. Okay? So when we look at velocity, we look at displacement over distance. We're really looking at centimeters per second. Okay? How much one molecule of water will move in 1 second. If we look at blood flow, we're looking at a volume flow over time. So obviously, if we look at our blue box here, there's a bigger volume in this blue box than this blue box. But they both moved at the same velocity, okay? So that's the difference between the two. We can look at it another way. Let's look at this, quote, blood vessel, unquote, where we have the same flow through the vessel. We have 3 different sections, A, B, C. The same flow in milliliters per second is flowing through this, quote, blood vessel. The same amount of blood that's entering is equal to the amount that's exiting. The flow is constant, okay? And you know that must be true, right? What goes in has to go out. All right. Now, if we look at section A, we have an initial velocity of 5 centimeters per second. And that's because the cross-sectional area of this vessel is 2 centimeters squared, okay? So the velocity is equal to the flow divided by the cross-sectional area. That's equal to 10 centimeters per second divided by 2, which is 5 centimeters per second. All right, 10 cubic centimeters is 10 mils per second divided by 2 centimeters squared, which is the cross-sectional area, gives you 5 centimeters per second. That's the velocity of flow. Now, the blood flow in B is exactly the same. but the velocity has dropped to 1 centimeter per second. V velocity is equal to flow divided by cross-sectional area. Flow is the same, 10 mils per second, 10 cubic centimeters per second, but now the cross-sectional area is 10 centimeters squared, and that gives me a velocity of flow of 1 centimeter per second. The velocity is lower here than here, despite the fact that the flow through each of these sections is exactly the same. Now we look at section C. Our cross-sectional area is now 1 centimeter per second, and our velocity of flow is reasonably high, 10 centimeters squared per second, 10 cubic centimeters per second, 10 mils per second, same flow as the other two, divided by 1 gives you 10 centimeters per second. So you can see the velocity decreased and increased with cross-sectional area, but the blood flow was the same. Okay, so what does this mean to the cardiovascular system? Here's your cardiovascular system. Blood flow is the same everywhere, 5 liters per minute. Okay. Notice the total cross-sectional area here starts relatively low because you're in your aorta. It's one vessel. It's a big vessel, but nevertheless it's only one. And now, as we go to our arterioles, look what happens to our total cross-sectional area. It goes up because now we're adding a whole bunch of arterioles and a whole bunch of capillaries together. Okay, and if you add up the total cross-sectional area, when you add up all those little vessels together, you find out that that adds up to a much bigger number than you had for the aorta alone. So the cross-sectional area goes way high as you go to the capillaries, and then it drops again as you go toward the vena cava. Okay, so the cross-sectional area of two vena cavas, superior and inferior, much lower than the cross-sectional area of all these capillaries added together. Okay, so what does that mean? When you look at the velocity of flow, it starts reasonably high in the aorta. It drops in the capillaries to a pretty low level because the total cross-sectional area has gotten so high. So the velocity of flow through the capillaries is pretty low, which is good, right? Because that's where all your nutrient exchange is taking place. And all that oxygen is being exchanged with carbon dioxide. All that stuff's happening through diffusion, which takes time. So you don't want a high velocity of flow through a capillary. And now we look at the veins again, they come back up, and the amount of blood being returned to the right atrium through your two vena cava is equal to the amount of blood that entered the aorta. And so this and this are the same. Okay, you have the same velocity of flow in both areas. The cross-sectional area is not too different. Okay, so the take-home message here: velocity of flow relatively low in the capillaries because the cross-sectional area, when you add up all those vessels, relatively high. Okay, so here's a summary of our circulatory compartments. The arterial pressure relatively high, the venous pressure relatively low, the microcirculation in between the two, so it's relatively intermediate. The resistance is high in the arterioles, okay, relatively low in aggregate in the capillaries, okay. It's high in the individual vessels because an individual vessel has a relatively small radius. But in aggregate, on a system level, the resistance to flow through the capillaries as a whole relatively low. And the venous resistance relatively low as well. The compliance is low in the arteries, high in the veins. The flow velocity, high in the arteries and the veins. These are your big vessels, so they've got a relatively low cross-sectional area, but you add up all these capillaries together, they make for a big cross-sectional area. We have a relatively low velocity of flow through the capillaries. The blood volume, highest in the veins, okay? This is where our reserve of blood is, and we can actually draw upon that when we lose blood volume, for instance, in hemorrhage, okay? And I'll explain how that happens in a later lesson, okay? All right, that's all I got on our comparison of our different compartments. In the next video, we'll start with a comparison of the different compartments one by one, starting with the arterial compartment. Thank you for your attention, and we'll continue on with the next video when you guys are ready to start it.